Now, one thing I promised yesterday that we would try to improve on the accuracy of estimates thing that's at the end of section 5.1. There, they give an explanation of why the difference between the upper and lower estimates, if the functions are always increasing or always decreasing, is the difference between f of a and f of b times delta t. Now, what I've done here is I just wrote down what they said using our brand new notation, right? The difference between the lower and the upper, if the function is always decreasing, then the left is the upper and the right is the lower. But if the function is always increasing, the left is the lower and the right is the upper. So the difference between the upper and lower, if the function is always increasing or decreasing, it talks like doublespeak, is just the absolute value of the left sum minus the right sum. And what they actually showed graphically is we have this much. I would like to change this just a little bit and then use it once or twice. Note, yes, delta t, remember what we do is we have a little graph over here. Can we see the graph? Kind of, yes. Let's just move it. Yeah, that's it, right? Right. It's what you get when you divide this up into n little pieces. So if I want the actual width of delta t, it should just be the width of the whole interval divided by the number of pieces. And we'll be using that for most of the semester. So let me put that in there instead. This is at the summary, I think, of section 5.1. So meanwhile, we have this. Like that. Now that is absolutely true. The thing about it is, what we've been doing all semester is if we have an upper estimate and a lower estimate, we don't use the left sum or the right sum or the upper lower. We took the average. So all I want to do at the moment is just write down, for example, if left was bigger and right was smaller, we've been using the average as being better than either one of them. And I think that's right. Now the thing about it is, left minus r would be this whole thing. We don't want, that won't be our error if we use the best guess. Our error will be half that. So instead of saying the difference between the upper and the lower is less than all of this, I want to be able to say the following, that our best guess error, what we've been calling our plus or minus error, we've been calculating this by taking the bigger one, taking the smaller one, and dividing by 2. And according to this, let's see here, this is supposed to be less than. Yeah, I like that better. Is less than, and this is what we're going to use many times over. F of b minus f of a all over 2 times b minus a over n. Now, what do we mean by the plus or minus error? That's the plus or minus error in using the average of the upper and the lower. This is actually much more useful, it's more accurate, and we're going to use it many times. Let's use it twice for our balloon problem already. Remember our balloon problem. Ready? Let's going to put this in the modern language we have at the moment. Yes, we were estimating the area under the rate graph of 8 times 0.5 to the t, like that, dt. And I'm going to use this thing twice. If n was 6. What we just wrote down says the plus or minus error is going to be less than, let's see here, f of b was what you got when you plugged in 3, that was 1, right, minus f of a, and that was going to be 8, the absolute value will fix that for us, and then we're going to get over 2, and then I get 3 minus 0 like this, and what are we going to get here? We're going to get 721, 10.5, does that sound right? b minus a over n. There it is. That made me feel better, yes. Okay, so the top is going to be 21, the bottom is going to be 12. Divide the top and bottom by 3, I'm going to get 7/4, I think. What does that say? That says if n equals 6, when we do all those big long calculations, we're going to get an error of 7/4, if I did that right. You notice we didn't actually have to find an estimate. This automatically tells us what our plus or minus error would have been if we had done the estimates ahead of time. This is unbelievably useful. This kind of thing gets used in computer science all the time because they always tell you that computing's cheap, and then when you want really high-powered computing, they'll tell you it's expensive. And so what they'll ask is the following thing. If we want the plus or minus error to be a lot smaller than 2 1/4, yes, how about something like 0.001? We're going to need a lot of rectangles. How many? And we can say, what should n be? What should n be? Well, going to run out of space here, but we're going to see what we can do. I can always go back to the top. We have this. We have that the plus or minus error is less than, let's see here, we had the 1 minus 8 on top, we have the 2 on the bottom, we have 3 minus 0, and ta-da, we have an n here. Now, this is what we want to do. They want the error, this thing over here, to be less than 0.001. I don't have any direct control over that. However, if I find n so that this is less than 0.001, then the plus or minus error, which is even smaller, will also be less than 0.001. So what we do is we put the 0.001 over here like this, and we solve just this part. So let me erase the stuff at the top so we don't smush. And I'm going to solve that for n. See, I have, let's see, that's going to be 7, that's going to be 21 over 2n. I want that to be less than 0.001, and I just want to solve that for n. I'm going to multiply n by both sides and divide both sides by 0.001. How about we do this? I multiply both sides by n, and then I multiply both sides by 1,000. So that's what we're going to do. I'm going to multiply both sides by n, and I'll multiply both sides by 1,000. So I'm going to get 21 halves over here like this. I multiply both sides by 1,000. Now when I multiply the 0.001 by 1,000, it's just 1, so I get this. Ta-da, like that. Yes, so that should be something like 21,000 over 2. I'm going to get 10,500 for n. Now what does that tell us? That says if we want a really good error like 0.001, right, we're going to have at least 10,501 rectangles. Notice we did not do a single estimate. The beauty of that, any error, the plus or minus error inequality is the ability to calculate what an error will be before we do an estimate, and also how many rectangles we're going to need if we want the error to be something specific. In some sense, it's absolutely amazing.